here, okay, and the FT is down there, okay. What we do is we use DC voltages, okay, to create the trapping, not RF, okay. The ions come in, we take the front section and we drop the voltage down. The ions enter, okay, they see the back section and they rebound.
What's a typical voltage on the back section, or when after they're trapped?
This guy might be like -3 volts. This might be like -1 volt and a volt. Okay. It's only a volt or two difference between the sections. It's very slight. The minute they come in and start coming back, we take DC1 up. So this is a quick drop and back up.
So they're pulsed and impacted.
Right. Okay. Exactly. Our electrospray is continuously making ions, so all those ions that are not being used are just lost. Okay. Now, inside, since DC1 and DC3 are higher in voltage than DC2, we create a potential energy well, and the ions sit in the bottom of the well. Okay. Now, the key is, if we just use voltage, this process is very inefficient. We capture barely 1 or 2% of the ions. So what we do is we fill the trap with helium. Okay?
But that's always there. You're not.
It's always there. It's never touched. Okay? It's ultra high purity helium. This creates the ball pit effect. Any of you guys with small children know what a ball pit is? You know, these big, huge things at McDonald's are filled with little plastic balls. The kid runs up and hits the balls and comes to a stop. We create a ball pit effect here. The ions come in and they start colliding with the helium, and the helium lowers their kinetic energy. And by the time they get about halfway through the trap, they're very cool, they're very low energy, and they don't have enough energy to escape out the back. So we trap between 35 to 70% of the ions that make it to the trap. So the ions that make it here, we capture about 35 to 70%, and we retain them in the center section.
So having that gas allows the voltages
to be very slight.
But does it allow longer time to trip? Does it slow down the kinetic energy of the ions as they come in to hit the helium? They make collisions, so they slow down, so maybe you can leave it open longer. In theory, shouldn't that be?
In theory, yeah. I don't know how much time it really affects. The biggest thing is, it's the kinetic energy. They have to have enough kinetic energy to get through DC1. We drop it, but we don't drop it down to 0. They have to have so there's a little bit of a bump. So these ions have enough energy to overcome the bump, and with that amount of energy, they would pierce right on through DC3, no matter what voltage we put there. So what we do is the helium slows them down inside, and when they come back, they really barely any of the ions have enough energy to come back all the way. And if they do, they experience a DC1 and just go back.
Because you have different amounts of times that you can build a trap for. Is that done in pulses, or is it continuous?
That's done in pulses. Okay. Now, once the ions come in, we raise DC1 and come back. The ions start doing this, and they keep colliding with the helium, and they slow down, and they go back and forth over 60% of the energy. So they go from about here to about here, just going back and forth in a simple harmonic motion. Does that make sense? So the first motion is our ions are just moving back and forth. They're walking forward towards DC3, and they're just rocking back and forth with Z motion. Okay. Harmonic motion, or axial motion. Okay, now, the next problem is we got to contain them in the XY dimension. So we don't want them to go out the sides or out the top or bottom. Okay. We apply an RF field at 1.2 megahertz to the 4 rods. This is called a quadrupolar field. A quadrupolar field is defined like this. This right here is the z-axis. So ions enter and would be ejected the FT along this axis. Okay. This is a 3-dimensional picture. This is not a 2-dimensional. Okay. So imagine this: the ions rotate around this axis, and this bowl coming into a 3-dimensional bowl. As an ion enters, if its motion deviates from the z-axis towards the x, or if it's towards the y, then the force, called the restoring force, pushing that ion back to the center increases quadratically. So an ion that goes like this would feel a little bit of motion. If he goes way over here, the force pushing him back to the center increases in force, and he just gets pushed back. If he goes too far, he goes back this way, he gets pushed back.
And then there's a potential, a static potential out, so it doesn't go to the FT. So here you have...
Right, because the DC is holding it this way. So the DC is pushing it in, the RF is pushing it in along the X and along the Y. Okay.
It seems like it would be uneven trapping along the path, the Z-axis, because if you get... Maybe I'm not understanding the fields here, but it's a cone shape.
It's a cone shape of force. This is not direction here. This is force. Okay.
So that line is drawn at some force level or something. Or
right. So if the ion is right along the z-axis, has no x motion or no y, then the force on that ion is 0, no matter where he is. Okay. If he's over here and he deviates a little bit, he experiences this much force. If he deviates this much, he experiences this much force. If he's here and he deviates that much, he experiences that much force. If he's out here, he experiences a lot more. So it's just the idea that the ion, when he's moving right along the z-axis, he has no force x, y. Okay. The minute he comes off of that z-axis, okay, towards the x-rods start pushing him. The further he moves, the harder they push him back. Okay. Does that make sense?
So they're doing like this figure 8 thing.
Ah.
What do they call it?
A longitudinal curve. It's a longitudinal curve. Okay, so we are looking down the z-axis. Okay. We have an x-axis or a radial axis, and we have a y-axis. And the ions are doing, this is not a figure 8. This is actually an ellipse that's pinched and wobbles. And when you look at it, it looks...
Here, can you do that again?
Yeah, it wobbles. And when you look at it from the right angle, it looks like you're looking at figure 8, but it doesn't cross. Okay? Now, everyone, you have this in your book. Flip to this slide in your book, because I need to draw some numbers for you. The problem is everyone envisions this figure 8, but they don't have the right vision of size in their mind. What page?
It's
Do you have this picture?
29, but there's no picture.
Oh! Draw that picture in your book. Do a rough drawing. Okay. Oh, no one brought pens or pencils, did we? At least you'll have one picture drawn. Okay. It doesn't have to be perfect. Okay. I'm not going to give you guys some award for having the perfect drawing. Okay. Now, the key is to understand the dimensions. Okay. When the ions are cool, because they've been colliding with the helium and they've been sitting in the trap for a few milliseconds, this y motion from here to here is less than 0.25 millimeters. Put that down on your picture. That's important. The dimension is less than 0.25 millimeters.
Between the two rods.
Right. Now the key is the slit height. The slit is 0.25 millimeters. So the y motion is smaller than the slit height. Okay. The x motion from here to here is less than 0.25 millimeters when the ions are cool.
Still less than.
So it's just
Still less than 0.25, right. So the longitudinal curve actually looks like a little circle, little sphere, kind of. Okay. But the x motion, with the z motion, which is almost an inch in length, causes the motion to look not like this, but actually look just like a line, because the z motion is so much bigger than the xy motion. Do you see that? Yes or no? Does everyone see that? This is key. You got to understand this picture.
because it's 4, the distance between the two rods is 4 or 4 point something.
Millimeters, yeah.
Compared to 0.25, which is like 5% of that.
Right. And the z motion is almost half the distance on the center section, which is about an inch. Okay, so they're doing this, and this motion is so small you don't even see it.